How many of you work in something reliability, infrastructure, platforms, engineering, whatever? Plenty of people, yeah, good. How many of you consider yourself a DevOps, maybe? Or SRE, maybe? Yeah, not many, good. Thank you, thank you. I'm an SRE at Google. SRE is Google's approach to...
It is!
Now we need to tell if it is too loud. Now I need not to talk too loud. Okay. Otherwise people will be deaf.
Little louder.
Huh?
Little louder.
Little louder?
Yes.
Okay. Is this good? Yeah. Okay. Let's see how it works. So yeah, SRE is Google's approach to scalable, sustainable operations through engineering work and practices. And this is where I work in. My name is Aleksejs, and this is work of quite a big team. So thanks to all of them. It is our SRE team I happen to be working in. And also Kraken team, people who work a lot on statistical foundation and computational foundation of all this. And all we together created this thing, or participating in creating it, or are happy users, or maybe not so happy users of it. So this is what I will be talking about. I am not a statistician, so it will be hard for me to explain some things, but there's enough statistics to put you to sleep. So stay awake. Right? If you have questions, raise your hand. Maybe I can answer something on the spot, and we should have time for questions and answers in the end. Despite the fact that we spend so much time fixing our equipment. So let's go for it. I work in Serverless, as I said. Serverless is absolutely cool. It is, you give us your source code or your container, we run it for you. It scales to thousands of instances in seconds. It scales down to 0, but you don't need it, so you don't have to pay for it. It is fault tolerant for you, load balanced for you. Everything is absolutely managed. You don't need to worry about it. It is cool, and our customers are using us for that. And we get very interesting cases like major sporting events, for example, when traffic suddenly comes up in a very big spike in a lot of requests per second, or QPS as we call them, queries per second, because this is our business model. I saw a meme one day which looked like a monitoring graph where there's a curve going like oscillating, 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 and shooting up. And the title of graph was "Traffic Team is watching World Cup." So this is how it looks from inside. We watch World Cup like this, or New Year, or any other big important event looks like this. So yeah, it is fun, and it is hard. How it all works, very, very, very approximately, not to the scale, but still to give you some perspective of what it is. What is the infrastructure I'm talking about? So somewhere here, we have your code instance which runs in something we call an app server, which runs on some server in some cell data center in some region, and there are very many of them. And there is also the control plane which you use to deploy your code, deploy a new version of your code, for example, to switch traffic between versions, to manage it in various ways. So this is what you use control plane for. And then you have users who are accessing your service, maybe it's mobile app, maybe browser, whatever. It is making connection to your app or your service. This request gets somehow onto Google Network, and Google Network needs to decide, okay, which region do I route it to, because users are anywhere in the world. And then you get to some region, and then in this region we need to decide, okay, which app server needs to serve, do we need to start the instance or not? So all this stuff is happening very quickly, and we are writing a lot of monitoring about it. Basically, every timestamp of every phase of the request arrival at particular points is being logged and also emitted as metrics to an in-memory data store of time series we call Monarch. And logs are just a big data warehouse queryable by SQL. Amazing how well it works given its size. And we have a lot of requests again. So this makes it especially hard. And then what can happen to it? So again, for you who work in something platforms infrastructure, do you get sometimes requests from your users saying something like, why is this thing slow? Why is my something running slow? Yeah, okay. How do you feel about it?
Good.
Yeah, it is. Huh?
They need to fix it.
Who needs to fix it?
Usually, it's everyone's responsibility.
Yeah, this is the trouble. Like ideally, the user should not have this question in the first place. It should not happen to them that this is slow. Or they should be able to figure out themselves why it is slow and fix it themselves, right? Or
So the user here is the user who accesses it, or the user who, like,
so
developer?
in this case, yeah, as a customer who deploys it.
Okay.
Yeah, yeah. It is not like particular users, I don't know, of Snapchat calling us and saying, why is Snapchat up is slow? No. It is Snapchat, and this is bigger trouble because they really think it's money. What happens here is, ideally, I would like to have an easy way to say, is it them or us? Like, who broke? Yeah? Us breaking them or them? And it is very hard to say because it can be very many things. It can be their change in something, and it may be a big enterprise with hundreds of teams, and some teams do not know what other teams are doing, and it is inadvertent result of changes. It may be change in their dependency. Like nothing changed about their service, but something downstream became slow, like database. Or it may be the user started doing something different, a new mobile app rolled out, whatever. And the traffic changed, and now their app behaves differently. How can I figure it out? I can't even read their code. Right? I couldn't possibly in quick time to figure it out. Then it can be something on our side. It can be some change in our platform or in some dependency inside Google, because we also have many teams changing stuff. Like it is not very easy to correlate it upfront. So it can be a noisy neighbor. It can be some other code running on the same CPU, consuming all of memory bandwidth, for example. And here you are, it gets slow. Like, how do you measure for this? It can be DOS attack going on. It can be our scheduling not packing stuff optimally enough and overloading something. How do we figure it out? This is very hard. Yeah, this is why we don't particularly like this kind of issues. And you get a ticket which says, my thing got slow, why? Right? And then you think, okay, it is just one customer, nothing is paging. Probably it's them who broke it. Then you join call with them, and there are like 70 people on this call, 4 hours, trying to figure it out. They can't. And you're like, okay, how do I tell them you broke it, you figured it out, right? And often you look into details, you ask them questions, and you find, oh no, it's us. It's actually us. Or you get another ticket, and another ticket, and another ticket, and another ticket, and you think, something is going really bad, right? And then you need to correlate it somehow. You need to find like, what is in common there, which is also very hard because dividing even one takes a lot of time, takes a lot of effort, digging through logs, analyzing stuff. So, and yes, we have a lot of logs. So why do we even make customers tell us this? Why can't we figure it out before customers told us? Why can't we figure it out from our monitoring data if this is our problem? If we changed something, if we broke something? So like a naive idea here is, let's take our latency distribution and call it an SLI and put some SLO threshold on it. And say, okay, every request slower than X is out of SLO, and therefore, if there are too many requests like this, it's a problem. We broke something. We tried it. Yeah, you just take latency distribution of our requests and plot it on a graph. This is log scale, so it is like 5 orders of magnitude of latency what customers apparently regard normal. They are okay with that. So where do I put my latency threshold boundary? Like at 100 seconds or so? And everything over 100 seconds is slow? Like websites having this latency will not have it ever. So what do we do? Naive approach doesn't work, right? SLOs set naively have limitations. What we can do instead, and we actually did, we take part of these latency, we take the phase which is from request lands to our infrastructure till it is delivered to customer code. We call it request delivery latency. We measure it. It mostly depends on platform performance. And, oh, this is interesting. Something changed. Somebody changed something. Okay. Okay. Let's go to first. And in this, we can be better sure of is it broken or not, because distribution is not that big. It is still quite big. But we can put some kind of a SLO threshold at X milliseconds, saying, okay, it should not take more than X milliseconds to deliver a request. And we can measure the ratio of requests over this threshold, and we can call it a SLO. It is still not enough. We tried. In this setting, you can have big customers or customers who have a lot of traffic drowning others out of their SLO, basically. Yeah, either this one big customer is unhappy, everybody is okay, or other way, they are happy and we don't notice everybody else being not okay because our biggest chunk of traffic is fine. So it doesn't work. Okay, we aggregate it per customer, per cloud project, and also per cell, because each cell can behave differently, each data center can behave differently. So we enter these different lines, different colored lines on different cells actually, and what this counts is number of projects in a cell which are out of a SLO at any given moment. And this, as you see, has some noise floor. So there are some customers for whom we don't know why it is still slow all the time. They are probably okay with it, they are not sending us tickets, right? So, but then this number suddenly changes, and this change means, okay, now our request delivery is actually slow for many customers. It gives me size of impact, scale of impact. It is very clear signal. What's the problem with that? The problem is it will not catch issues with latency in any other phase of our request latency. It doesn't capture end-to-end customer experience as such, right? And this is what we are after. How do we do it? It is impossible to do this, exactly this, use exactly this technique for every phase of request processing. We need to do something different. Now let's get back to our goals. Like what we want. So we want a metric that represents customer experience, whole of it, ideally, that is combinable, that we can measure across all the fleet, all the projects, and total up in some way. And talk about like percentages and ratios of impact, the customers or regions or whatever. We want to be able, obviously, to correlate multiple customers having a problem with particular components, for example, which may be causing this problem. Yeah, to get also some kind of causal analysis out of it, this would be ideal. It has to be very cheap to compute because we have a lot of traffic, we need to do it very quickly. And ideally, it should be based on some principles rather than arbitrary thresholds we have chosen looking at the data empirically, but rather some principles that are clear and not disputable in a way. So going back to basic principles, the fundamentals of it, reliability is basically availability, performance, and correctness. We are after this. How do we do it? So in practice, availability approach, the naive one is just to take a ratio of requests that are taken against all requests. This is your availability. We tried it, as I said, it doesn't work that well. It doesn't work also because there are errors we cannot attribute clearly. It may look like user error, but it may be actually system error. It may be error created by the system. There are deadlines which have no specific error codes enough. There are malformed requests, there are retries. Users will retry on errors, so your errors will spike up even more. Okay. Similarly, for performance, we can try to create probers and send some SLO on tail latency, but probers are probably only some specific use cases which do not cover all the breadth of what the users are doing with the platform. It doesn't work either. And for correctness, we need to have tests, and we have them. We have a lot of tests. We have cast checks preventing evidently bad changes going out, push stops when it starts breaking something, but it is still not enough. We want to do better. We don't want to hope that it will be fixed by itself. But what do we do? applying this idea, we are trying to look at the service, and we see that this service has a very big distribution of latencies, a lot of events. It is very hard to make sense out of this seeming noise. But interestingly, from customer perspective, it looks different. When the customer looks at the workload, what they see is some performance they observe normally, and this is usual performance for them, right? And then there is another customer who also sees some other performance, and it is also usual for them. So there is this perceived reliability as perceived by the customers, which is based basically on past performance of the system. And they expect it to stay the same, right? So tickets we get about why did it change, actually. They never send us tickets when it gets faster. This is like one-sided change, but it is a change. So how can we detect it? This is the question. We can measure for each workload this latency distribution, and this looks something statistical. You probably saw such graphs in some statistic textbooks. This is what we want. And what we care about in this case is this latency latency measurements to be self-similar, basically to be stationary, to remain, the distribution to remain the same over time. And if we can see that, say, over a week, for example, distribution remains the same, then we can expect it to stay the same in the following days, right? This is the idea. And this means every workload becomes our property. We know what latency to expect for it. We can measure it when new requests come in. And if this latency deviates too far from expected distribution, then there is an outlier. If there are too many outliers, something is going wrong. This is the idea. This is what we call the 2 sigma technique. Why 2 sigma? You will learn a bit later if you actually manage to understand everything before and not fall asleep. So, how does it work? As I said, we have this hypothesis that self-similar workloads will have stable performance even in the future as well. What we do, we partition all the versions. We call a version deployed by a customer, a version of a service or an app, a cohort. And for this cohort, we approximate this distribution, and we get distribution parameters, and we store them. We call it the baseline. And then, for each new request, we can measure if we can test statistical hypothesis that this particular measurement is from this distribution, and get some kind of probability, is it or not, right? Which is very, very useful. And we do it based on solid statistical principles. There is nothing we are kind of inventing here, right? Which is amazing. And what we get is just time series of likelihoods of this data being outliers, of these latencies being outliers. And this is what we are. So this is how it works roughly. We have this batch process that splits everything into cohorts, every measurement that computes baselines based on distributions we manage to fit. And we store it in a database, and then we measure data that's coming in. And for this data, we can say, okay, this is that far on distribution curve. And the question is, how far, right? And what is great is this measurement of how far it is from the mean. We take this measurement, we measure it in standard deviation, which is the same measurement for every workload. It does not depend anymore on how slow or quick is customer service. It is the same unit of measurement, which has very narrow distribution, very narrow. It's very easy to notice change, right? So this is basically mechanics of it. Yeah. So what we do, we specifically look at how many requests have latency beyond 2 standard deviations, beyond 2 sigma. This is where the name comes from, right? From the mean. And statistics tells us that this should be normally distributed, and for normal distribution, there should be 2% to 5% measurements in this area. If you get 10% there, well, we evidently have a problem, right? We need to do something, and this is great. This is amazing. And on this, we build data products. We build monitoring, we build alerting, like this one, for example. This is a real monitoring dashboard. So what do we do for each project, for each workload actually, but then we can total it per project. We can calculate percentage of requests which are outliers. We know this percentage should be below 5. Okay, should be below 10. Let's say below 10. Yeah, if it is over 10, we have it. And then we can say that this is a percentage of projects which have increased latency. And this is what this graph says, basically. It says something like, yeah, this line is 50% of projects. And it says, okay, at that point, 50% of projects had 8% of outliers instead of 2 to 5. They probably noticed. And 30% of projects had 30% of outliers, which means they very likely noticed. Tickets are incoming. They just had no time to send them, but monitoring already noticed it, right? Maybe their page is not paged yet, but we know, yeah, this is like the best case we are aiming for, yeah, to notice it and fix it before somebody else gets paged. Okay, so far, very clear, I hope. Okay, and this also leads to simple enough impact analysis for on-caller. If you get an alert for this, you can immediately look at number of projects experiencing unusual latency. Unfortunately, you see, there is some kind of noise floor all the time, because again, statistical models do not fit perfectly what we are measuring. But here it evidently shoots up. So it is this difference are the projects that normally had no trouble, and now they have. Something changed. Now we can go figuring out what, now we can go declaring an outage, we can involve more folks, more teams, get them working on it depending on how high it is, how bad it is, how it is distributed. If it is in a particular location, we can drain the location. So there are things to do right now. Right? Okay. Before I get to your questions, there are a few that we get asked frequently. So yeah, does this actually follow normal distribution or log normal distribution or what? Well, we tested. And if it doesn't fit, then we need to find another distribution for it. Yeah, similarly for our approximations, we back test the whole model. Like there should be a slide about everything somewhere. We test on past outages, basically. We try to confirm that this would have detected past outages. Cohorts are defined based on different versions of services deployed by customers. Infrequent workloads is an interesting case. This was an arbitrary choice. Basically, we decided something like, if you're sending to your service less than 1 request per day, do you have high expectations of latency? Like, do you care about 2 milliseconds or 10? Probably not. Like, we can't measure it at that precision. You need to send few requests per day. Yeah, and this is backtesting. So this is a real outage where we had 1% of projects practically off, and another 4% like every 5th request failing. And this is fine-tuned based on the SLO thresholds we have selected. This one is just this latency thrown at statistical models without any training, anything like that. It just works, which is amazing. Limitations. It is hard for people to understand graphs about these percentages of projects having percentages of a SLO meeting or not. Like, eventually we removed practically all of it. We compressed it all in something very simple for encoder. Like, this is the number of affected projects, ratio of affected projects, you deal with it, right? We have hidden most of this statistical information. It's not actually relevant for incident mitigation as such. Distributions that we use to fit latency. Distributions were fitting like half of our traffic roughly. At the moment we created this, and the moment these slides were created, since then we added a couple more models, so now this is better. But even with half, it is enough. we have not found, I think, cases where this half we are measuring was not affected at all, and another half was suffered. No, if we have a problem, it is quite well distributed across many customers, so it is not. And maybe biggest problem, but it is by design. This is symptom-based. The difference between symptom-based and cause-based is symptom-based alerting and monitoring is based on customer experience. It tells me customers have problems, which is very valuable. It doesn't tell me what part of infrastructure is causing this problem at all. I have no idea. And this is very hard to correlate, especially latency. Like errors are a bit easier if you have good error attribution, if you invest continuous engineering effort in keeping good error attribution. This is hard, but there are solutions to it. For example, this is what BigQuery is doing, because actually this is applied at Google not only in service, not only in cloud run functions and engine we run, but also at BigQuery, for example, in database products, where they build similar models for each phase separately, and then they correlate them. And then you can say something like, okay, total time went up, and this is where I/O time also went up, which means I/O is causing this trouble. Yes or no? No, it is not causation, it is correlation, right? But engineer knowing architecture of the system, or LLM agent for whom you wrote a playbook explaining architecture of the system can figure it out, right? And this is where it will work. So we are doing things like this, yeah? We are also doing things like correlating how many customers see increased latency for requests going through this particular app server, or through this particular networking component, for example. And this also tells us something, oh, this component may be overloaded because everything on it became slow, or many things on it became slow. And same things running on other things are not slow. So, okay, do something like that. This is slow. Yeah, this is hotspotting. This is classical problem of hotspotting. We use it for experiments, for A/B testing as well. So you can roll out experiments with part of your population and then compare the same graphs or the same data and see if you see difference in latency. It is very, very good for it. So here we are. Yeah, we built a tool that gives us a reliable measurement, which measures what customers really care about, which is latency stability, which is combinable, which can show us correlation with what should not be correlated, like with something getting slow in some other place, for example. And this is amazing. I will not spend more time on the Sigma. Yeah, and there are obviously more publications from SRE and Google if you like reading books. And questions? Wow, that was great.